Hope you guys can see my screen. Good morning from California. My name is Jiaxi. Thank you for joining us today virtually. This RAS webinar. I'm very honored to speak regarding my latest research to study the railway network dynamics with the yard simulation, especially including those mainline interactions and the resource constraints. So I assume most of our audience are from the transportation sector. So you guys probably familiar with the knowledge that rail is competing with the road transportation in terms of the market. And if you ask a customer, what's the most important thing that you guys want from transportation? They probably say they want reliability. They want their goods to be reliably sent through the network and arrive at destination with a reliable time frame. However, unfortunately, the freight rail is considered generally less resilient than the road transportation, which we're competing with. And it's pretty easy to think why, because first of all, we have a pretty much less dense network with less alternative routes that you can select from. So for example, if you want to choose send goods between 3 nodes in the network, the origin A and intermediate stop B and destination C. For the rail option, you normally don't have a direct route between A and C, and you have to send your train from A to B, and then eventually B to C. And at those Bs, it's usually called those clustering yards where you have to completely disassemble your trains and assemble them again at those yards and spend the
speaker.
And spend a relatively huge amount of time wasted within those intermediate stops. And alternatively, for the truck options, you usually have more options of routes you can choose. Usually not only have direct route between A and C, you have multiple routes, you have highways, you have those, different smaller roads.
Can you hear me? Yeah, okay, now I think I cannot hear. I cannot hear.
Can everyone else hear me?
Yeah.
Okay.
Yes.
Yep.
Good. So with that smaller network and less resilient network, if you look at the interaction or interconnections between the mainline and the yard within the network, we could find that if you have one part screwed up within the network, it usually not only solely impact the location where that disruption occurs, but in turns, it actually will impact the other portion of the network. For example, if you have a derailment in the yard, you will not only reduce the yard capacity, but you will also reduce the mainline capacity, and that reduction of the performance on the mainline will actually have a feedback system and have further impact on the yard again. So with that, such a network, we always want to ask questions: how does the congestion and the consequence of derailment within one clustering yard propagate through the whole mainline, and how does it impact the adjacent yards within the network, and then how does it impact the mainline, and in fact the whole network if you consider the system dynamics, for example, for this big network of the BNSF with those major hump yards. So to answer that question, let's start with a smaller subset of network. We start with 3 hump yards with the connecting main lines. So we choose Pasco, Northtown, and Galesburg to start with. And then you will have trains that run between those pairs of the destinations. And in addition to those pairs of trains between destinations, you will also have trains arriving and depart from those yards and then connect to outside of the model network. So with such a network that was simulated, if we have a derailment at Northtown, and the direct impact we can imagine is that, if you derail at the hump, all the operations are shut down. You cannot depart trains anymore, so that all the train departures are delayed from schedule. And for the long-term impact, since the hump is not processing more trains into the classification bowl, those trains arriving in the receiving yard cannot be handled anymore. So they will start to have a queue within the receiving yard, and eventually when the receiving yard is full, you will start to have the queue outside of the Northtown yard. Therefore, those trains arriving to Northtown from Pasco and Galesburg will start to line outside of Norristown on the main line, causing a queue outside. And after the derailment is removed and the service is resumed in Norristown, the Norristown is starting with a very full initial condition, and the Norristown will process an additional extra processing rate or speed to handle that leftover or hangover traffic. So in that case, the Norristown will try to arrive and depart as many trains as possible to handle those additional traffic. And with that additional arrival speed and additional departure speed, the traffic arriving in Pasco and Galesburg from Norristown will also relatively increase, so that Pasco and Galesburg will start to also experience a surge within the inbound traffic, and so that the performance in Pasco and Galesburg will also be impacted. And eventually, Norristown get rid of all those traffic that congested during the shutdown and resume normal departure rate or departure schedules. And eventually, that resumption of the operation will be spread through the mainline to the other two yards, Pasco and Galesburg. That's where we would witness and define the whole network as recovered from the derailment within the Norristown. So to simulate such a complicated simulation, to simulate such a complicated network, I proposed a simulation model with the AnyLogic. So AnyLogic is a discrete event simulation tool where you can import or draw your track structure and then code your traffic flow in details and define how your traffic flow moves through your pre-drawn track structure. So this is showing an example of the single hump classmeter model built in AnyLogic. And other than the single yard representation, we also have the mainline representation. So we have two models actually proposed for the mainline representation. The preliminary model, where we assume double track between those hump yards on the main line. So for the double track, because there's a plenty space for trains to pass and meet on the main line, we usually can assume there is a minimum travel time between any two pair of destinations. And in comparison, if we consider an advanced model, where we consider single track and resource constraints, we can expect there would be an additional delay for this congestion on the main line and the additional delay that we can observe from the constraints in resource. So to further explain why there is a congestion delay, let's look at a typical meet and pass on the single track corridor. So this chart is showing a single track corridor with two trains of two directions, the blue train and the red train. So now all the trains are running on the single track corridor. And if you want to have the blue train and red train to meet, you will have to arrange it on one of the sidings. So basically have the blue train, which usually has lower priority, to wait on the siding and wait a short delay for the red train to pass so that the blue train can continue its journey. But if we consider a different condition where the siding that we normally schedule the meet is blocked by another train, with this situation, the blue train cannot meet the red train at that siding anymore. And in comparison, that blue train needs to stop in advance, wait for an additional extended delay at the siding for the red train to go all the way to meet. And that's where we will experience the congestion delay on the main line. And so that we have this congestion delay on the single track corridor, we can also extend it to a huge corridor, basically the whole single track section between two yards. So we have 2 yards, yard 1, yard 2, and there is single track corridor, and we have a bunch of sidings along the track. And similarly, we have a red train and blue train that want to meet in the middle. And for this condition, we can arrange the blue train to stop at a siding that the blue train needs to wait the least amount of time for the red train to pass, to meet. And however, if we have a derailment occurred in yard 1, and the trains are queued within the receiving yard, and then also there is a queue of trains to arrive the yard outside of the yard one. In this condition, the blue train again cannot meet at the original siding. It has to wait in the earlier sidings, wait for additional time for the red train to pass. That's where we will say we had a congestion delay on the main line because yard one is full and congested. And after yard one, the derailment at yard one is clear, the hump resumes operations, so we can receive trains from those queue outside the main line again. We will take others trains to arrive in the yard. And in this case, the blue train may or may not have chance to move to the earlier siding before it can meet the red train. So in this case, the blue train may or may not have the congestion delay due to the impact of the derailment in the yard one, although the derailment is already clear. So to be able to analyze and quantify what is the congestion delay for the trains whenever there is a derailment in the yard or whenever there are trains blocked on the siding, a separate experiment was conducted with RTC, which is a typical mainline railway simulation used by a lot Class 1 railroads. And we simulated a network with 19 passing siding for 240 miles. We also simulated a 41 passing siding with 400 miles network. And we have fixed intervals between the sidings, and we have sent trains for both directions within the network and see what is the average delay for the trains to experience given different number of sidings blocked. So this chart is plotting the incremental delay, basically how many minutes a train has to wait additionally on the siding if given different number of sidings blocked. And surprisingly, we notice that the total length of the network doesn't really impact this result. Or in other words, it doesn't matter how big the network is, the additional delay the trains are experiencing are solely dependent on how many sidings are blocked or how many sidings sidings are blocked and the train cannot park up. So to generalize this results, we can fit the linear line as a two-sectional linear regression with this simulated result, and so that with less than 7 number of sidings blocked, we have an equation where we can generate how many minutes the train will delay on average on the main line. And we also have, if there are more than 7 sidings blocked, we can also calculate how many minutes the train is going to be delayed on the main line due to that congestion delay. And similarly, we also have the resource constraints that could cause additional resource delays. And to set up the model, there are road engine resource constraints, the crew engine resource constraints. So for the road engine, it's assumed that each arrival train will bring in one set of road engine, and those road engine will conduct a 1-hour service, and after that, the engine will be available for other usages. And any outbound train depart from the yard will need to have one set of the road engine to be able to depart, and the engines are non-directional. In comparison, the road engine is more complicated. The arrival train brings in the road crew, and after 12-hour rest period, the road crew will be available again. And those road crews are actually directional. For example, a crew from the crew that traveled from Norristown to Pasco will have to return to Norristown. And so with that situation, we'll have different 2 sets of crews, but each has serving one direction for each of the Class 1 yards. And for the situation where there are trains queued outside of the main line, the crew will bring the train, park on the siding, and the crew will move to the rest period. And when it's that train's order to arrive in the receiving yard, there will be a road crew assigned to take that train in the receiving yard. So basically, try to repeat whatever the reality is for those resources. So that with those resource constraints, we can expect whenever there is shortage in engines or crews, the trains will have to wait until those resources are available so that you can experience an additional delay for those resource constraint delays. So after all those things coded, here is the demo of the network model with any logic. So basically, it has 3 hump clustering yard model running simultaneously. Each hump yard model is running on their own individually with detailed traffic flow. And other than the 3 hump agents, there is also a mainline dispatcher agent to calculate the travel time between 2 yards and schedules arrival in each yard. And there are also other data collection agents where you can monitor performance, such as the number of cars on the line, the dwell time for the real car in the yard, and the mainline delays. So with that network model, let's design experiments to study the resiliency or the propagation of the impact of derailment from north-south to other 2 yards and the whole network. So this presentation will be focusing on the advanced model where we apply the single track corridor and the resource constraints. So there are 2 variables of interest, the daily throughput volume per yard, which is reflecting the saturation level of the whole network, basically how busy each yard is and how busy the whole network is. And we're also interested in the disruption duration from 12 hours to 96 hours. So basically, how long does the hump last? Is that 12 hours? Does it take 12 hours to clear the derailment, or does it take 96 hours to clear the derailment? And they will have different impact on the propagation of that impact. And for the baseline parameters, each yard will be given a initial crew, and the number of the initial crew and engine is decided in those prerequisite experiments. So basically, I will run prerequisite experiments and decide how many exact number of crews and engines each yard need to successfully warm up. And then each yard will be given exact number of crews and engines. So there is no extra or no shortage to start with. And for the network simulation, there are 16 trains inbound per yard per day and 16 outbound trains per yard per day. And then each carries 1 block. And those train arrivals from the outside network, those train departures will follow the predefined schedules. So output metrics, we want to simulate the derailment in north-south. And given that derailment occurs and that given the different length of the disruption duration, we want to know what is the recovery time that measures the time between when the service starts to degrade and then the service recovers. So let's see some results. This plot is showing the impact propagation within the whole network. It's plotting the number of real cars on the network over time. So if you look from the left, you can see the simulation model starts with empty and idle. There's no real car within the system to start with. And then at 120 hours, you can see it becomes relatively stable, where the network reaches a steady state at about 120 hours. And at 240 hours, that's where we apply the disruption or the derailment at north-south. And in this case, what you can observe is that the number of real cars on the mainline and the number of real cars in the total network increases. That's because, again, the north-south cannot handle more real cars because the hump is shut down due to the derailment. The cars will start to queue within the receiving yard and eventually on the mainline adjacent to north-south. After about 312 hours, we remove the disruption at north-south, and takes a long time, another extra 400 hours if you don't take any actions. The real cars queued on the mainline outside of Northtown will be slowly taken into the Northtown yard and be processed. And about 700 hours is where all those queues on the mainline are resolved, and there's no more backlog of real cars on the mainline due to that disruption. And then eventually, after another 500 hours of slowly recovery, you can see where the yard network recover. So this is what happens if you don't take any action and let the system slowly resolve itself. And let's compare this result with an earlier experiment with the preliminary model, where again we don't have the single track corridor or the crew constraints. So we have double track, there's larger space and there's infinite number of crews and engines to supply. And with this case, you can see the recovery time is actually only 510 hours compared with 1,200 hours when we apply the additional 2 constraints. So that's where you can see, the impact of the single track corridor and the impact of the resource, the crew and engine constraints are really hurting the resiliency of the classroom yard, or really deciding the resiliency of the classroom yards. So another performance metric we can collect is the real car dwell time at each yard. So again, the model starts with empty and idle and get steady at about 120 hours, and this disruption occurs at 240 hours, and we'll remove it at 312 hours. You can see the real cars throw a huge amount of time in Northtown because those cars arrive either right before or during the disruption, so that it has to wait the whole time until the disruption is removed and then start to move. So you can see they observe the real cars in Northtown observe a huge average dwell time, and after about 990 hours, the real cars in Northtown recover to its average performance or average real car dwell. And if we zoom in this chart to look at the other 2 yards, you can see the Galsburg and Pasco also have an increment in the average dwell time after some amount of time of derailment removal. And the Galsburg yard is faster to respond than Pasco yard, which is because Galsburg is closer to Northtown than Pasco, so it takes shorter time to transport or propagate any of the impact through the mainline. And then with this jumping chart, you can see that Galsburg recovers actually after Northtown at about 1,200 hours, and the Pasco recovers even 20 hours later than the Galsburg. So that was showing the example experiment where we can collect the average dwell time and number of real cars online and look at the chart and decide how long does it take to recover for each experiment. And we actually repeat the experiments for 4 levels of throughput volume and then 8 levels of disruption duration. And for each experiment, we collect the recovery time needed for each yard and for mainline. And then let's see what is the impact of those factor levels on the recovery time of each part of the yard. So this chart is plotting a fixed throughput volume, so the fixed given number of real cars processed and arrive and depart within each yard, and we vary the service disruption from 12 hours to 96 hours. And the y-axis is plotting the recovery time needed between service degrades and service recovers at each part of the yard. It's a really interesting chart. There are basically 3 different things we plotted: the network, the mainline, the Northtown, and Pasco and Galsburg, which are very close to each other. So let's look at the 2 easier, simple lines to look at: Northtown and mainline. You can observe the time needed to recover is basically proportional to the time, the duration of derailment. So the longer it takes to clear derailment, the longer it takes to recover at Northtown and mainline. And for Pasco and Galsburg, it's actually showing a gap or a jump in the middle. So before the jump, if you close Northtown for less than about 48 hours, the Pasco and Galsburg recover pretty quickly, actually recover faster than mainline or Northtown. And however, if you shut down Northtown for longer than 48 hours, Pasco and Galsburg becomes slower to recover. So the potential reason potential explanation is that if you shut down Northtown for short term, although the departure, the train departures are paused in Northtown during that disruption, because it's relatively short time, the derailment impact is mostly propagated to the Pasco and Galsburgs through the batch departure or the additional longer train size after Northtown starts to resume operation. However, if Northtown is shut down for long term, the supply of the engines and crews from Northtown is paused long enough that Pasco and Galsburg will start to experience shortage in crews and engines to depart the train to other direction. In that case, if you shut down Norristown for long enough time, the Pasco and Galesburg are basically experiencing a secondary disruption because there's no supply of the resources. The operation is also paused or shut down until Norristown recovers, and then we start to supply engines and crews to Pasco and Galesburg, where they can start to resume normal operation. And for this chart, another thing we can summarize is that for Northern Mainline, because it's basically a proportional relationship between the time to recover and the duration time, we can come up with a new definition of recovery rate, which is basically the slope of those lines that indicates the time needed to recover the service for any incremental disruption hour. So North-South and Mainline has a constant recovery rate regardless of the duration, and Pasco and Galesburg will have two recovery rates, one for short disruption duration and one for long disruption duration. And we also can repeat that for the super volumes to study to find this recovery rate in terms of the service disruption given different saturation level within the yard. So we start with 960 cars per day per yard, which is quite low in terms of the saturation level. And also did the 1280 cars per train per day and 1920 cars per day per yard. So very similar. Norristown and Mainline, the recovery time is always proportional to the duration of disruption, and the slope, which is the recovery rate, is independent of the disruption duration. And Pasco and Galesburg, they always have a two-section in terms of the recovery rates, one for short disruption duration and one for long disruption duration. And another thing you can observe is that if you increase the saturation level within the yard, that gapping point or that changing point of the recovery rate at Pasco and Galesburg becomes earlier. So basically, the more saturated the yard is, the impact of resource and such as crews and engines will be increased within those yards, because the more traffic you have, and they're more sensitive to any of those constraints as well. And now we have the recovery rate for North-South, Mainline, Pasco, and Galesburg, basically each part of the yard at different throughput volume. What if we plot that recovery rate as a function of throughput volume? What we got is that the recovery rate is exponential to the throughput volume. So basically, the more congested or the more saturated your system is, you will be expecting an increasing impact in the recovery time needed for the system, regardless of the disruption duration. And this result can be compared with the other recovery rates that we generated with no resource constraints, or the recovery rate we generated for the single yard simulation. So let's look at the resource constraints. When the network doesn't have resource constraints, you can see that the recovery rate is substantially lower, which indicates that, again, the resource constraints are playing a very important role in impacting the resiliency of the system. And another thing we can observe is the single yard model, where we only have a single north-south transfer yard. There is no Pasco and Galesburg, and there's no mainline. There's no crew or engine constraints. This is how long, what's the recovery rate it needs to, this is the amount of hours needed to recover any additional disruption hour. And you can see that the single yard, which is Northtown itself, recover much faster than the Northtown when there is a interaction or the feedback impact from the network or the yard. And lastly, let's do a sensitivity study in terms of those resource constraints, which is very, it's a very popular topic within the industry. Again, as I said, before the experiment, I did a prerequisite experiment to decide what is the exact number of crews and engines required to start with, which is called initial resource level. And let's change that initial resource level. So basically, when we start the operation, how many crews and engines we give the yards. Do we give more than what the yard needs to start, or do we give less than what the yard needs to start? And let's look at the result for a sample experiment with 1,600 cars per day per yard and 3 days of service disruption. So the first performance we're looking at is the recovery time, which is the resiliency of each yard in the network. You can observe that if you decrease the initial resource level, basically if you don't give enough engines and crews to start the model, afterwards, if you have any service disruption in Northtown, those 3 yards will fail to recover. So basically the whole system will crash and you will never be able to recover given the insufficient number of crews and engines circling around within the system. And alternatively, if you increase the supply of the resource level and have a bunch of ample or additional surplus crews and engines to start with, you will observe the decrement in the recovery time, which is the improvement in the performance. And another thing I can observe is that there is a decreasing marginal benefit if you keep supplying additional resource. Like you can observe a 50% of increment or improvement in the recovery time if you give only a quarter of additional engine crews. But if you give basically infinite crews and engines, basically when there's no constraints at crews and engines at all, the increment isn't much substantially increased compared with giving only 25% additional resource. So there is a decreasing marginal benefit that the industry should consider when they decide to invest additional crews and engines within the yard, to find where's the point that your investment gives the best of benefit. And recovery time for mainline has actually similar trend. If you decrease the resource level to start with, the recovery time needed for the mainline will increase. And if you supply the additional crews and engines in each yard to start with, the recovery time needed for the mainline will decrease as well. And another performance metric I look at is the dwell time. We have the average dwell time during recovery and the average dwell time during normal operation. So surprisingly, the dwell time isn't super sensitive to additional crews and engines if you give additional of them. But if you decrease if you reduce the initial resource level by giving less crews and engines, you will expect longer dwell time during normal operation and during recovery, which makes sense because again, the preset initial resource level is the exact number needed to maintain normal operation. If you give extra, it won't have huge impact of normal operation because those additional crews and engines basically are just sitting with no task actually assigned to them. And lastly, we're also interested in the maximum dwell time for each part of yard, which measures the worst performance of the system. And with this case, the maximum dwell time during Northtown is not sensitive to the resource because that maximum dwell time is basically how long the real car needed to wait for Northtown, needed in the Northtown yard to wait for the hump to reopen, which is directly related to the length or duration of service disruption. But in comparison, those maximum dwell time during recovery in Galsburg and Pasco, they are decided, but they are caused or originated because there's no enough crew and engines from Northtown. If you supply additional crews and engines to those 2 yards, you can expect the worst performance being improved in that 2 yards. And if you decrease the initial resource levels in each yard, you can see that it's also a damage in the or the increase in the maximum dwell time, which damaged the worst performance. So if you look at all of them, the recovery time is actually the most sensitive to those crews especially if you're not supplying enough engine screws. When you don't have enough engine screws for a yard you're operating, you might be fine during normal operation with not huge amount of decrement in your level service. But whenever there's any disruptions or any disturbance, your yard will be very fragile to them, and actually potentially might fail to operate properly during those extreme events. So industry operators, be careful when you supply your crews and engines within the yard or within the whole network. And so quick conclusions. This experiment studied the service disruption at a hump yard within the network, which caused congestions and performance degrades in the network. And those impact is usually transported or propagated through the delayed departure trains and variabilities in the departure train size. And the time to recover, which is the time between service degrades and the service recover, is found to be linearly related to the duration of service disruption. And the recovery rate, which we define as the hours needed to recover service for any incremental disruption hour, is found constant, which is independent of the service disruption, of the duration of the service disruption. And when we apply the mainline congestion and resource constraints, it's notably slower to recover, which again emphasizes the necessity to consider those network interactions and the resource constraints when we study the resiliency of the railway network. And also, increasing the throughput volume or the saturation level will exponentially increase the recovery time given the disruption. So basically, when the yard or the system is near saturation, the network is more fragile to any potential disruptions. And lastly, from the sensitivity study of the resource levels, providing not enough resource will significantly harm almost all performance metrics, especially during the disruptions. However, adding the resources will only provide partial improvements, so there's no point investing infinite crews and engines to the network. So thank you for your attention. Thank you for joining us again. I'll be answering questions.
Thanks, Jiaxi, for the interesting presentation. We do have a couple of questions that in the Q&A and in the chat. So I will go through these questions, and then we can take over some questions that from audience that they may, some of them may still have. So one of the questions that I can see is from Milan, that it is not common that delay increases linearly. It is common to increase more proportionally. So are there analytics behind these calculations?
Which slide are you talking about? Sorry, I was looking for the meeting chat. That question wasn't in the meeting chat, right?
Yes, in the question is in the Q&A. Are you able to see that?
Hold on.
Yeah, there are 3 in the Q&A, and there are a couple of in the chat.
Okay, I'm not seeing anything in the Q&A.
Okay. So yeah, so Q&A that we have some questions regarding the delay increase linearly or proportionally, and what is analytics behind this calculation? Is Milan still here?
Gotcha.
Yeah.
You're talking about the congestion delay analysis from the RTC experiment, if you're still here. I actually don't think he's here anymore. But to answer that question,
yes,
finding
actually you have here linear relationship instead of commonly exponential topics in these cases. This is the queuing process, and it's I don't know how analytics have you used for getting these all calculations, you know. And of course, what is missing from the whole presentation, in my opinion, is that you haven't defined the terms. For example, what is the capacity of shunting yards? What is the capacity of rail lines? What are capacity of sidings? How these things are influencing each other? What is the critical point in shunting yards? Is this the kill, or is there or these are accepting trucks, or let's say leaving trucks or something like that, you know. So in presentations, first, I think that you should define the terms you are using. That's first. And second, to provide at least minimum analytics, how you have calculated things. In that case, many things will be much clearer, and these kind of questions would not be needed to be asked.
Well, thank you for your comments. Most of things in this presentation is not calculated. It's generated from simulation. So it's basically look at the results and write it down in an Excel file and plot it from Excel directly. So for example, this congestion delay analysis, the chart on the left are each dot is a data collection from, or each dot is a experiment with data collection from the RTC experiments. So for example, the last dot of the 500-mile network, that is the data collection, or the data output to run the 500-mile network with 40 sightings blocked within the network. And then you look at the result of the RTC, and then write it down, and then plot the results over the controlled experimental parameter that you changed. So you get this chart on the left. And because we want to be able to generalize this direct simulation experiment output, and I want to be able to know what is the exact incremental delay for train given a number of block sightings. So you just do the linear, you just fit the linear regression model over the simulated results, and then you can get a equation for each, or you can give an equation of, in this case, two equations to calculate that incremental delay given a number of block sightings. And for the rest of the simulation, for the rest of the slides, those are all simulation outputs. Basically, simulation will give me an Excel of the hours, number of route cars on the each part of network, the yard, the mainline, the network, and then as a function or given each simulation time, so you can plot it. Thank you for your comments. And regarding the basic information of the yard, although I wasn't talking about the capacity of the single yard, the yard capacity is about 225-60 cars per day per yard. So when we're looking at 1,600 cars per yard for those sample experiments, it's talking about 62.5% of capacity.
Thanks, Jiaxi.
Not wanting to interrupt again you, but how much of these calculations are realistic? How much are they realistic? Are they close to the real life developments or not?
If you're talking about the how reliable or how
realistic, not reliable, realistic.
Okay, the realistic of
real life.
Yes, thank you. Because the time constraint, I wasn't really talking about how this yard simulation model was validated or verified through the realistic situation, but basically when I developed the simulation model, there are experiments to verify and validate the realistic and the feasibility of the yard, to compare the simulation result with published study, as well as time and motion study that basically field observation. And since you're also from the rail industry, you probably also know there is basically no open public data for any of those major class yard or mainline. And that's exactly why we want to choose simulation, because there's no, first of all, you cannot drill your actual knowledge ton yard for 72 hours just to get a experiment result. That's exactly why we need simulation to conduct experiments to answer questions that you cannot repeat in real life. And that's very hard. Simulation models are known to be very hard to be validated through real models or real work or realistic yards. But best we could do is to validate the experiments or validate the simulation before, validate the model itself before we run additional experiments to study different what-if questions or conditions.
Thank you, thank you, thank you, thank you.
Thanks, Jiaxi and Milan, for the question and answer. So we have a couple of questions in the chat. One is a question from Soya that it can be observed that slope is changing in each case. And how about constant in each case, disregarding to the slides 28, 29?
What do you mean by constant in each case, if you're still here?
Hello,
Yes.
can you
Hi.
hear me?
Yes.
If you go to the slide 28, I guess, or 29, 28. Yeah, here you compare the slope of slope in each case, it's changing based on the rail capacity and then hours of the disruption. So how about the constant for the recovery time? Is it the constant recovery time for all cases, or is it changing, and how is it changing?
Thank you for that question. It's a very good question. The constant does change given different throughput volume, which does also make sense. We have different saturation level of yards. Just let's think of an extreme case. You have a yard that is 30% full, and you have a yard at 90% full, and your constant will be basically where you how long do you need to disrupt the yard so that the yard has any impact at all. So you can imagine if for a 30% full yard, you probably need to disrupt or shut down the whole yard for a longer time for the yard to show any impact at all, compared with when your yard is 90% full, where you have probably 10 minutes of disruption, just a random number, probably 10 minutes of disruption, then your yard will start to have impact, and that will be where the constant and for this chart. So that, yes, constant will change with different throughput volumes, but to me, that constant is less of interest because it really depends on what's your setup or what's your operation parameters, what's the strategies you're using within yard is less interesting than the slope, which you can generalize it and find for example, you have a yard, you get a chart like this with this such type of which the slope, and you'll be able to predict how long the yard will need to recover given an X hours of duration, and then you can decide what mitigation strategy you use or implement. So yes, the constant does change over different throughput volumes, and it wasn't analyzed here because to myself, the slope is more of interest.
Thank you.
Thanks. We have next question from Carl. Have you compared the model result to changes in actual performance after unscheduled shutdown of the hump at the major class yard? And how frequent are such accidents?
Well, good question, Carl. I do want to know that too. Unfortunately, the only data source I can get are those news where you consider, a huge snow or extreme weather that shut down a yard and then caused huge impact. But I don't really have data from any shutdown in actual yard, and they won't, of course. And also another thing is this experiment is assuming no mitigation strategy. And the operator is just letting the trains interacting letting each yard interacting themselves, and then that's why you can observe a 2 months time frame to recover disruption for them to recover from a shutdown of 3 days, which is really unrealistic. And this is just looking at the extreme conditions where what happens if you don't do anything at all to the yard when there's unscheduled shutdown. which I don't think any of our smart class 1 railroad actually does. They would definitely implement strategies to either reroute trains to other yards, or doing some other operations. And if there is any data open to me, I'm more than happy to study the next step of this experiment, to study how does different mitigation strategy impact impact the resiliency or the recovery or the propagation of those impacts. So throw me some data if any class 1 wants to keep sponsoring this study, although I already graduated. And how often are such accidents? It depends on the slope or the duration of the disruption. Based on another of my study to analyze the frequency of derailments in classroom yards, it's actually quite often. I would say, if not like once a day, in those classroom yards. Maybe more frequent than that or less frequent than that, and usually it takes different time to clear the derailment based on where derailment happened. It could take 1 hour, 2 hours if you simply can remove a real car, and then it could also unfortunately cause, again, as I said, 3 days or 7 days if it's a huge snowstorm. And again, and also the location of derailment also matters a lot. If a derailment occurred right on the hump, that will stop for the yard, but if the derailment occur on one of the classroom tracks, it will have minimum impact of the overall derailment. So again, this experiment is talking about the extreme conditions or the extreme situations where it's a huge impact. It's basically the worst location of derailment you can expect, and then the bureau is not doing anything to help with it. And we just want to see what is the interaction pattern between each yards and the main line, because to my knowledge, there's no study in North America that has been studying the exact interaction between mainline yards. Most study will be focusing on the mainline, very minimal study actually look at yards at all. So thank you for that question. Again, anyone has data, please shoot me an email afterwards if you want to talk.
Could I just comment? I've been working with railroad major class yards for more than 50 years. It's hard for me to say that. The only incident I know that is in the magnitude of what you're talking about have been in weather-related delays. So hurricanes that wipe out all traffic in New Orleans for a couple of days, and the railroads had to reroute around that hub. And then the blizzard of '78, which shut down almost the entire northeastern United States for a week in the beginning of February, and Conrail took 3 months to recover. So your notion that if you have a shutdown of a hump for 3 or 4 days, it may take 3 or 4 months to recover, that is true. On the other hand, I don't recall a single incident at any yard, haven't heard of one, where a derailment on the hump caused a major shutdown. If there is one, there may have been 1 or 2 over the time. Most derailments would be somewhere else in the yard. In terms of the disruption, there was a discussion from Milan about the capacity versus the volume. And I think that's something that you could really pursue, because the problem is that as traffic is not, it's no reservation service. So when traffic booms or there's poor weather or cold weather and processing slows down, you can have a situation where 1 or more yards is trying to operate 2,000 cars a day, but the capacity is dropped to 1,700 cars per day through the yard, and that delay will propagate. And that's very common. And I suggest that you're up in Canada now, talk to CN about how yards get clogged and what actually happens, and then see if you can compare your model or simple queuing models to get the results. But I like to see someone working on class yards. As you say, there hasn't been much. There has been quite a bit of work. I've done work on the interaction between yards and terminals, but you have to find it. Thank you.
Thank you for your comments. It's interesting to see there's actually 1 yard took 3 months to recover. That's crazy. Yeah, if there's any confusion, derailment here is basically a terminology where I chose, and then it probably really should be replaced by disruption. It could be any disruption. It could be a hump retarder failure, or track failure over hump, or machine shutdown at the hump towers. It could be anything, but it can be more generalized than actually hump derailment over hump, which, as you said, it only had probably once ever. And also, there are similar experiments I did to study those derailment at pull down. So I did try to study different derailment locations and see what's the differences in the impact of those derailments at different locations. But thank you for your comments. And regarding the recovery rate, the definition of recovery, yes, the technical definition is basically the performance metric we're looking at comes back to a certain percentage or standard deviation of the average value of that we collected before disruption. So yeah, as you can see, it takes a really long time for the tail end, at the tail end of the chart, where the yard is kind of recovered, but really but it's still adjusting. So that depends on what slope we want to look at. If you want yard to recover to all right, or recover to a stage that is basically recovered, yeah, you can cut that. You can collect data at that point. But to me, I really want to know how long does it take to exactly recover, which is basically recover by above and below 5% of what the average value was. And I was really interested in what is going on within the tail end, and it turned out just very small interactions between yards. So basically, like a 10 car extra length in train size might cause those tiny tail ends. And to railroad, it probably it's not even a problem, having a train 10 car longer than planned. But as a study, I want to try to keep it as strict as possible. Thank you for that question. And 2 more, let's see. Some parts might need to leverage or machine learning. I think we're short in time. I can reply from emails if you prefer that, and close the session.
I think we can address the last one question. So there's one
Okay.
for the machine learning and operation, and about between networks.
Yes. So this study is not just as it is. I don't just run. I don't just develop a simulation model or run a bunch of experiments, and who knows if it's even close to reality. The whole point of simulation, as I said, you can run experiments that are not possible in real world. You can generate huge data where you probably don't have from the real industry, and those can very much be the input of machine learning, which is like a new trend, simulation assisted machine learning models. So given someone else who might have a machine learning model and machine learning study that he wants to be able to predict the recovery time or predict the departure delays in a classroom yard given a derailment happen somewhere else, they probably don't have the data to actually be able to learn it, to study it, to train their machine learning model. And in that case, a simulation tool is a very not only possible but good way to provide those big data to fit in the machine learning models, if that makes sense. But to do that, you got to make sure your simulation model is generating correct data, good data, because you basically make up a data set and fit it to machine learning. You have to make sure data you're providing is good enough, and that will require lots of verification and validations through the model. But thank you for that question. It's definitely not only doable but worth it to adapt the current model we have to any optimization, further optimization method. For example, we can also study what is the optimum solution to help Northtown, or to, if possible, redirect trains or reroute trains that are still on the way to avoid Northtown if Northtown is disrupted for unknown time. And that would be another study that might be interesting. And that has been commented.
I think Jiaxi, also explain a part for the last question, that about the
QA
simulation.
networks thing. Yeah, thank you for that comments. Yeah, there are lots of QA models in the literature review, as you can tell, and I myself actually did use some part of the queuing theory in other chapters in my dissertation to study study the impact of the surge volumes within the yard, and to those surge volumes, or the additional volumes, as long as you can generalize your question into there is a increase in the arrival rate or there's decrease in the departure rate, those questions can be converted to a queuing theory question. Yes, that's very true, and I did use it, and it was really close to the simulation result when I compared the queuing theory I developed and the experiment result. And yeah, I could use the queuing networks, but it was quite hard. And this was the last chapter of my dissertation. I really wanted just to wrap it up at that point, but that's a good suggestion.
Yeah, thanks, Jiaxi. We have remaining comments and the references from Carol about some of those references that might be helpful. And thank you very much, Dr. Jiaxi Zhao, for giving us this presentation on looking at the impacts of disruption events on the yard operations. And thanks everyone for attending. We will continue host the Informs webinar, and I look forward to seeing everyone for our next webinar.